Greetings! Welcome to Electronic Circuits 1. I am Behzad Razavi and this is lecture number 15. Today we will continue to look at how we can use a bipolar transistor to build interesting circuits such as amplifiers. So if you recall, last time we attempted that, and today we would like to pick up from there and see what happens. Just to refresh your memory, let's take a look at our lecture material last time. We said that a bipolar transistor is usually biased or placed in what we call the forward active region, and that is defined when the base emitter is forward biased by means of a battery, and the collector base is reverse biased perhaps, and that's also guaranteed by another battery that we connect between collector and emitter. So we saw that the collector current that flows has an exponential dependence upon the base emitter voltage, as shown here. Typically this -1 is negligible, so we usually drop it off and we just have Is x above VBE over VT for the collector current. So that shows the sharp dependence of the collector current on the base emitter voltage, which is actually useful, as we will see later. Now, because the bipolar transistor is a three-terminal device, we can measure the currents, for example, when we change one voltage, but we have to keep the other voltage constant. So in this test, the collector emitter voltage, this one, is constant, but it's this one that's changing. Now we can go the other way around. We can keep this constant and change this one and see what happens. Now, looking at the physics of the device, we might decide that the collector voltage should not affect the current that's flowing from the emitter to the base through the junction. And that's more or less true. So we would expect that for a given base emitter voltage, as we vary this voltage, as this goes up and down, the collector current is constant, provided that we are always in the forward active region. So provided that this junction is never forward biased. All right. However, we can also observe that if we perform one test and we have this much current, then we can step this voltage to a new voltage, VBE2, and have a different current. So this plot gives us a lot of interesting information. It says that the current does not change with the voltage. The current drawn by this transistor does not change with this voltage. And that's an indication of a current source, an ideal current source, the way we saw it in basic circuit theory. So if I place all of this into a box and I have only two wires coming out, I can call that box a current source. Also, it says that this is a voltage-dependent current source because I can have this much current if I pick this internal voltage to be VBE, or I can have this much current if I increase the internal voltage. So it is a voltage-dependent current source. So now that we know a bipolar transistor is a voltage-dependent current source, meaning it generates a current in response to a voltage, we can go back to our original vision of an amplifier. If you remember, when we started out, we said, well, if I have a voltage-dependent current source and I connect it to a resistor, this entire circuit can become an amplifier by proper choice of K times RL. So why don't we replace this voltage-dependent current source with a transistor? So we replace it like this, and what we expect is that if we connect some sort of signal here, let's say microphone signal, so the signal that's going to this microphone from my voice, and give it to this transistor and connect this resistor like before, we should have a voltage at this output that is greater in swings than what the microphone produces. And that's what we will call an amplifier. So today we will revisit the circuit and realized that the way we have constructed it actually doesn't work. So we have to modify the circuit to have an amplifier. So first, I would like to show you what's wrong with this circuit, and then see how we can fix it. All right, so today, this is what we would like to do. We revisit that simple amplifier and see what's wrong with it. Then we try to fix it, and that brings us to the concept of biasing, which is very important in amplifier design. Then we go to the concept of transconductance, yet another important measure that tells us what a bipolar transistor can do and what it cannot do. So one step at a time. All right, so here's what we would like to start with. So simple amplifier revisited. All right, so let's draw the amplifier again. I have a bipolar transistor that receives the microphone signal at its base emitter junction, and then goes to a resistor and delivers a current to the resistor. This is a voltage-dependent current source, so its current flows through this resistor and generates a voltage. Okay, all right, so this is our microphone, and that's our bipolar transistor. And let's say that the bipolar transistor satisfies this equation as we know. And let's say IS is 5 times 10 to the minus 16 amperes, as an example. So IS is equal to 5 times 10 to the minus 16 amperes, a typical value for bipolar transistors. Okay, well, what we know is that this current is given by this voltage over the resistance, so it's V out over RL, and this current is IC. So that tells us that IC must be equal to minus V out over R, because KCL has to be satisfied at this node. So we say IC is equal to minus V out over RL, and that means that V out, the voltage of interest, is equal to minus RL times IC. And IC, the collector current of this device, is given by this expression. So IS exp of VBE over VT. Okay, I have an extra parenthesis here, don't worry about it. So that's the equation that we have. That's the precise equation. All right, so this equation tells me that if VBE changes because of the microphone signal, then V out changes. So potentially I can amplify the signal. So let's say that the microphone generates a signal as a function of time, and starts from 0 and goes to maybe 10 millivolts. So 10 millivolts. So it starts from 0 and goes to 10 millivolts. That's the signal coming from the microphone. And our hope is that when this 10 millivolts, 0 to 10 millivolts, goes to the base emitter of the transistor, it generates a current. This is the current that it generates. That current flows through the resistor, gives us a voltage. And that voltage, hopefully, is amplified. So, for example, if this goes from 0 to 10 millivolts, maybe this voltage goes to 100 millivolts. We have a factor of 10 amplification. There's a negative sign here, but we don't worry about that. That's not that really important. Okay, so let's see if that actually is possible. All right, here we go. Because the base emitter voltage is now 10 millivolts, right? The microphone signal is 10 millivolts. I have to put 10 millivolts here for VBE. VT is 26 millivolts at room temperature. Calculate this exponential, minus 1, multiplied by IS, which is 5 times 10 to the minus 16 amperes. And see how much current we get. All right, so right here, you should hear an alarm in your head, because I am saying that the base emitter voltage is 10 millivolts. Right? The microphone signal goes from 0 to 10 millivolts. So the base emitter voltage is 10 millivolts. Isn't that awfully small? From what we know, the base emitter voltage, which is a diode, is about 700 to 800 millivolts. So we are giving it only 10 millivolts. So something will probably go wrong. But that's okay. Let's move forward and see what happens. All right, so if VBE is 10 millivolts, I can write this as V out equals minus RL times 5 times 10 to the minus 16 amperes times e to the 10 millivolts over 26 millivolts minus 1. Right? Now if you calculate this entire collector current, what you find is how much? You get 2.35 times 10 to the minus 16 amperes. So is the current small or large? It's very small, right? It's very, very small, 10 to the minus 16. And that's not surprising. We gave the base emitter voltage only 10 millivolts from the microphone directly, and as a result, we got a very small current. All right, so I am looking for an output voltage of maybe 100 millivolts in response to this 10 millivolt swing provided the microphone. 100 millivolts here. So this needs to be 100 millivolts. This current is this much. So what do we need for this resistor? You can imagine that this resistor has to be very large. So in fact, if you calculate it, this tells us that RL, so let's say V out should be 100 millivolts as an example, or minus 100 millivolts. Then RL has to be, I calculated that to be 4.25 times 10 to the 16 ohms. Okay, so now we see what the problem is. The base emitter voltage sensed a 10 millivolt swing from the microphone. The collector current goes up to 2.35 times 10 to the minus 16 amperes when the transistor senses only 10 millivolts for the base emitter voltage. This current is very small. For this current to be multiplied by a resistance to give us, for example, minus 100 millivolts, that resistance has to be extremely large. This is not something that we can build ordinarily. This is not something that would be practical. What's the practical value for a resistor in this type of circuit? A few kilo ohms, maybe a few tens of kilo ohms, but not more than that. So we are very far from what we should be using. So that tells us that this is not an amplifier circuit. We cannot build it like this. So that poses an interesting question. How do we fix the circuit so that it can actually amplify a 10 millivolt swing coming from the microphone? All right, so let's draw the IV characteristic of this transistor, IC versus VBE, to see what's going on in this case. All right, so here's what we have. IC as a function of VBE. So what we have done so far is this. We have an exponential characteristic, and we allowed VBE to change by 10 millivolts directly from the microphone. So 10 millivolts might be here, right? So we allowed the VBE to go from 0 to 10 millivolts. And as a result, the current that we got was tiny, 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 right? That's the current, and that current is this much. So that's a problem. The 10 millivolts of 4 volt bias for the PN junction of the base emitter gives us a very small amount of current. All right, so then how do we fix this? Well, what I'm thinking is perhaps if I change the color of my pen to something else, what if I do this? Instead of applying the microphone signal directly to the base emitter voltage, let's play a game. Let's do this. We take the microphone and it's going to the base emitter of the transistor, but I will place a battery in series with the microphone. So here's a battery, and I connect it like so. And I pick some voltage, some constant value for this battery. Let's say 750 millivolts as an example. So 750 millivolts as an example. Now the rest of the circuit we copy. So we have our RL, and then we are interested in this voltage. So V out, and we're hoping that there will be a current here, IC, and so on. The question is this different from this? Or is it better? So what does this do, this battery? Okay, so for the moment, let's say I am not speaking to the microphone. So the microphone produces nothing. The microphone produces 0 volts. 0 volts means from here to here 0 volts. It's just like a short circuit, right? No voltage. So that means that the base emitter voltage in the absence of a signal is 750 millivolts. So let's go find that on this plot. 750 millivolts is somewhere around here. Of course, this is not to scale. And at 750 millivolts, we have a certain current. How much current do we have? That's not that hard, right? We have 750 millivolts without any signals. And IS is 5 times 10 to the minus 16 amperes, so we can find IC. And IC in this case comes out to be 1.7 milliamps. All right, so far, nothing exciting has happened really. All I did was calculate the current through the transistor when the microphone produces nothing, 0. And we see that we have this much current. But now, let's suppose that I do talk into the microphone, and the microphone generates a 10 millivolt signal. So now, this guy has 10 millivolts on top of 750 millivolts. So we are sitting at 750 millivolts because of the battery, and the base emitter voltage suddenly goes from 750 to 760 because the microphone generates another 10 millivolts of signal. So we go from 750 to 760, so again we increase by 10 millivolts just like before. And this brings us here to 760 millivolts. At the moment that the microphone signal has reached 10 millivolts. Okay, how much current do we have for 750 plus 10? We can calculate that again, and what we see is that the current through the transistor is equal to 2.48 milliamps. Is it expected that this 10 millivolt increment and this 10 millivolt increment give us different increments in the current? Yes, because this is not a straight line. It's an exponential function. So the increment in current here is much smaller than the increment in current here. All right, so is this situation better? Well, now when the 10 millivolt signal from the microphone comes in, the current goes from 1.7 milliamps to 2.48 milliamps. So the current increases by how much? The difference between these two. So this is 780 microamperes, right? Okay, so you see now that the current change here in response to the microphone signal is much larger than what we had before. Before, we got only this much current after the microphone signal was applied. But now we have this much current with the signal from the microphone applied. Okay? All right, so if I have a 780 microamps of increase in the current as a result of the microphone signal, what resistance do I need here to produce 100 millivolts of signal at the output? So that's not that hard, right? So you see RL is equal to, we need 100 millivolts of signal at the output divided by the increment in the current that the microphone has produced. So 780 microamps, and this comes out to be 120, let's see, I had the number here, 128 ohms. 128 ohms, a very reasonable amount for resistance. So previously we needed this much resistance, now we need only this much resistance. So let's take a step back and see exactly what happened here. So what we see is that the bipolar transistor is not capable of amplification if we just give the signal directly to its base emitter voltage. The signal is small, the base emitter forward junction is very small, the current is extremely small, so we can't have any voltage at the output. Right? This is not usable. But if we superimpose the signal, the microphone signal, on top of a constant voltage, so we superimpose the microphone signal on top of a constant voltage, and then we give the result to the base emitter, now we start with a respectable current. This is a pretty good current, 1.7 milliamps. And then when the microphone signal comes in and makes a change, we go from here to here. This change is large, so the resistance that's needed to convert this to 100 millivolts of output voltage is a reasonable value. All right, so if we look at the base emitter voltage as a function of time, while we are speaking to the microphone, this is what we will see. So let's plot this base emitter voltage as a function of time. So here's the base emitter voltage as a function of time while we are speaking into the microphone. So if we don't speak into the microphone, we have a constant value of 750 millivolts, right? So 750 millivolts. But once we start speaking into the microphone adds its own signal to 750. So if I change the color to maybe this, what we see is that the signal keeps going up and down with the microphone signal. So because we already have 750 and hence 1.7 milliamps of current, the transistor has enough strength in it, so to speak, that it can take this tiny fluctuation of, let's say, 10 millivolts and give us a large voltage at the output. All right, so this is a very important concept. Now, the act of adding this voltage here, as we went from here to here, to provide a certain base emitter voltage in the absence of signals is called biasing. So this is what we call biasing. It means provide proper voltage and current so that the transistor can amplify or perform other functions, but at least for amplification, that's what we need. Now, sometimes when we ask our students in tests or quizzes, why do we bias transistors? They just write to make them work. But it's more than that. What does it mean to make them work? It means that we want to establish a certain amount of base emitter voltage and a certain amount of collector current without any signals, so that the transistor is ready. And when the signal comes in, that signal can create a significant change in the collector current and then produce an output and so on. All right, so that's what we need. So it's important to understand that when we say proper voltage and current, let me add something here. In the absence of signals. So the microphone signal, for example, is not applied yet. We're just looking at the constant base emitter voltage and constant collector current. All right, so we will play with this idea. We'll incorporate this idea in many, many circuits to come. But right now, we're just trying to build the foundation for why biasing is necessary. Okay, let's go and introduce one more concept. The other concept or the definition is called operating point. And operating point is defined as the values that we have chosen, for example, for the base emitter voltage and the collector current in the biasing task. So again, without any signals. So operating point means the values, the bias values chosen for VBE, IC, and other quantities that we will see later. For example, this is our operating point. 750 millivolts of base emitter voltage and 1.7 milliamps of current. That pair defines our operating point. So VBE equals 750 millivolts, IC equals 1.7 milliamps. All right, so that pair is our operating point. Okay, all right, so that's what we have in terms of biasing. And now we are ready to go ahead and make some observations. So let me draw a line here. I would like to summarize all these concepts and step by step clarify the points so that as we go along, everything is clear in our mind. Let's change the color to brown. Okay, so observations. Oh boy, sometimes this pen goes a little crazy. Observations. Number one. What we have seen is that the bipolar transistor is a voltage-dependent current source. So we say a bipolar transistor can act as a voltage-dependent current source. So that means its collector current changes in response to its base emitter voltage. Okay, so that's what we have learned so far. The next observation is that the operating point for example, this value of base emitter voltage and this value of collector current determines how the transistor responds. We said it responds to the base emitter voltage. But how? Well, if the operating point is 750 millivolts and 1.7 milliamps, and then we bring in a 10 millivolt microphone signal, it responds by a change in the collector current equal to 780 microamps. On the other hand, if the operating point is 0, 0, right here, that's an operating point, right? And a signal comes from the microphone with a 10 millivolt amplitude, then the response is terrible, right? The response is very, very small, it's not usable. So the operating point determines how the transistor responds to this base emitter voltage change coming from our signal source. It could be a microphone, it could be something else. All right. The third observation is that, rather the third question, the third point here is, which operating point is better? Now I'll put this in quotation marks. What do we mean by better anyway? But we have a feel for what that means. So I will draw two cases for you here. Here's actually maybe just one case. All right, so here IC and VBE. Here's our exponential characteristic, just like before. And let's go to blue. All right, I will pick operating point number 1 as before, 750 millivolts and 1.7 milliamps. So here's the first operating point, 750 millivolts and 1.7 milliamps. Okay. All right, so we will call this case 1. Operating point number 1. All right, but this is not unique. I can pick some other value, right? So let's go ahead and pick some other value. So let's change our color to back to brown. So here we go, VBE, IC, and then same exponential, but this time we go to, for example, 770 millivolts. And how much is the collector current? Well, we have 770 millivolts, we have IS, we can find IC, and that IC is equal to 3.6 milliamps. 3.6 milliamps. We will call this case number 2. All right, so here's our quiz of the day. Which one of these cases is better? Now you decide what we mean by better, and then you decide which case is better. I will give you 90 seconds to think about it. All right, so what is your conclusion? Well, what we can do is, again, apply our microphone signal on top of this bias value and see what kind of response we get from the transistor in its collector current. What we do remember from our previous example is that a 10 millivolt change on top of 750 gave us 780 microamps of change. So we will write that here. So 10 millivolt change gave us 780 microamps of change. So this is a 10 millivolt change, and that's a 780 microamp change. How about here? If I increase this by 10 millivolts, again assuming that the signal from the microphone is added to this 770, then what happens? So we increment this by 10 millivolts. So the microphone signal brings the VBE from 770 to 780. How much current do we get? Well, plug in 780 here. We have IS, we can find IC. So IC in this case comes out to be 5.3 milliamps. So this value is 5.3 milliamps. So we see that the change in the current as a result of the 10 millivolt increment coming from the microphone is 1.7 milliamps. 1.7 milliamps. So which case is better? Well, what this tells us is that a 10 millivolt increment from the microphone gave us 780 microamps of increment current response, if you will, in case 1, but 1.7 milliamps of current in case 2. So case 2 has a better response, has a stronger response to the microphone signal than case 1. In other words, if I let this 1.7 milliamp change flow through this resistor, like the value before, I get a larger voltage than what I got before. This resistor value and 780 microamps gave us 100 millivolts. But now, this resistor value and 1.7 milliamps will give us a larger voltage. So that means that the amplifier will amplify the signal to a greater extent. All right, so what we see, this is a simple trend. What we see is that as the bias value of the base emitter voltage, this battery, assumes larger voltages, larger values, right? As we go to higher values, the collector current becomes more sensitive to the base emitter voltage. Here, we got nothing. It was very small. Here, we got something. Here, we got even more. So as we give it a greater base emitter bias voltage, the sensitivity, the response, the change in the collector current increases. So that's great, and we have to see if we can have some sort of metric that describes this behavior so that we don't have to write these numbers all the time. And that metric is called the transconductance. So let's go to another page and we'll see what that means. Just remember that we are looking at how much change we get here for a given change here, if we have a bias of 750 or if we have a bias of 770, etc. Very well, let's go add a page and see what we get. All right. Okay, so this brings us to what we call the concept of transconductance, and we should go over that. That's also a very important concept that comes up in all of our studies. So concept of transconductance. So transconductance. Okay, so what we have seen so far is this. If we have IC as a function of VBE, and of course, always in forward active region. Then we have an exponential function. And what we see is that if we start from some value and increment, we have a certain increment in the current. If we start at some other value, some higher value, and increment, we have a greater increment in the current. So an increment in the base emitter voltage gives us an increment in the collector current. What do we call that anyway? This increment divided by this increment, what is that called? That is called the slope of the characteristic, the derivative of the characteristic. So what we see is that the derivative of the characteristic, the amount of change in the current we get for a given change in the base emitter voltage, let's say 10 millivolts, becomes larger and larger as we go this way. The slope of this exponential increases. And of course, that's a property of exponentials, nothing surprising. So then why don't we define the slope of this characteristic as a metric that tells us how sensitive or how strong or how responsive the transistor is. So we write the derivative of the current divided by, with respect to the base emitter voltage. This is called transconductance, and it's denoted by G sub M. So this is what we call transconductance of the transistor. So I hope by now it's clear, especially from the previous example, that the transconductance tells us how strong the transistor is. Here we change the base emitter voltage. Let's say microphone signal comes in, we get some change in the collector current. Here we get more change in the collector current. So the transistor is a better amplifying device here than it is here. And that's what we define as the transconductance, the slope. So this slope is lower than this slope. All right. So we will play with this a lot in the future, but this is just a basic definition. And let's calculate the transconductance from our previous cases. So if I go back to the previous case, I can just write the transconductance values here. All right, so can I calculate transconductance for case 1? Well, we have a certain increment in the current. Can divide that by a certain increment in the voltage. That will give us a transconductance. Will it? Well, we just have to be careful that the derivative assumes a very small change here and a very small change here. If this change is not very small, then the derivative is not accurately calculated. Is 10 millivolts small? We don't know yet. So for now, let's just say it's small enough, right? We don't know, but let's just say. So if I just go with that, if I calculate the slope as this change over this change, then this tells me that GM1 is equal to 780 microamps divided by 10 millivolts. 780 microamps divided by 10 millivolts. I will write approximately here because we are not sure if this is a small increment as needed by the definition of derivatives. So that comes out to be, of course, 0.078. 0.078. What is the unit? The unit is amperes over volt. Amperes per volt. Amperes per volt has a name in electrical engineering. We call that Siemens. So this would be Siemens. And the symbol for Siemens is capital S. So capital S. Not to be confused with lowercase s. Lowercase s is used for seconds. Uppercase S is used for Siemens. Okay, that's our estimate of the transconductance of the transistor here in case 1. What do we expect in case 2? Well, we expect the slope to be greater, so we expect that GM2 will be greater. Let's calculate GM2. GM2 is equal to 1.7 milliamps divided by 10 millivolts. So that comes out to be 0.17 Siemens. As expected, this is greater than that. All right, now these are both approximations because I don't know if this increment is small enough. But hang on to that. We'll come back to that in a few minutes. All right, so we calculated transconductance in these two cases, and we saw that indeed as we go higher up in the curve, the GM increases. GM1 is over here, GM2 is over here. Okay, very good. Now, can I find an equation, an expression for GM itself? Well, I know the dependence of IC upon VBE. So let's go ahead and take the derivative. All right, so GM is equal to derivative with respect to VBE of IS exponent VBE over VT. So I'm dropping that -1 here. So the derivative of this is just 1 over VT. So that's easy. We get IS over VT times exponent VBE over VT. So that's an equation that you can always remember for the transconductance. All right. So how does the transconductance vary as a function of VBE? It's just an exponential, right? That's all. So the transconductance itself, GM, as a function of VBE, is an exponential function. Not surprising, because an exponential function's derivative is also an exponential. Okay, but actually we can rewrite this in a simpler form. How much is IS exponent VBE over VT? That is the collector current of the transistor, this one. So why don't we just replace that with IC? So GM is equal to IC over VT. So that's a beautiful, simple relationship that tells us how the transconductance of the device depends on the collector current. It's very simple. So if I plot GM as a function of IC, then it's very straightforward, right? So GM as a function of IC is a straight line. So one simple number to remember is the following. If IC is 1 milliamp, then GM is 1 milliamp at room temperature over 26 millivolts. And sometimes we approximate this by 1 over 25. So sometimes we actually write this as 1 over 25 ohms. Or you can write it as approximately equal to 0.04 Siemens. These are all the same thing. Sometimes we prefer to write it like this, sometimes we prefer to write it like that. Doesn't matter. It's all the same thing. Okay. All right. So that is how we obtain the transconductance. And again, this all goes back to the notion that we are looking for the strength of the transistor, for how well or how much it responds to a change in the base emitter voltage when, for example, a microphone signal is applied to the base emitter voltage. Now, this tells us why our very first simple amplifier failed. Our very first simple amplifier, which we had here, failed because we're down here. How much is the transconductance of the transistor down here? Well, we started out with 0. When VBE is 0, IC is 0. When IC is 0, the transconductance is 0. So the transistor really doesn't have any strength, any sensitivity to base emitter voltage changes. And that's why we had no amplification. The circuit was pretty useless. So that's what we observe here. GM as a function of IC is 0 here, right? So when we have no bias, when we don't give any bias to the base emitter voltage, we don't have any transconductance, we don't have any amplification, that's it. All right, so the key point here is with no bias, IC equals 0. That means GM equals 0. That means no amplification. All right, so in other words, we can say the objective of biasing a transistor is really to create the right amount of transconductance. If you don't have bias, transconductance is 0, no good. How much transconductance do we need? We need a certain amount. So for that, we need a certain current, we need a certain collector current. And for that amount of certain collector current, we need a certain amount of base emitter voltage. For example, 750 millivolts. So that's the logical thought that we have. So we say for amplification, need a certain GM, which means we need a certain IC because this is related to it. From there, we need a certain VBE because for the transistor, we have a relationship between IC and VBE. And this pair defines the operating point of the transistor that will give us the amount of transconductance that we need to have amplification. Very well. Let's take a quick look at these results. So I said that the transconductance is given by IC over VT. This is the slope. The slope here, if you have this much IC, the slope here, if you have this much IC. So now I can go back and compute GM accurately for case 1 and case 2 and see what I get. In other words, was my approximation valid before? Remember, I said GM1 is this much and GM2 is this much, but this was 10 millivolts of change, maybe not a very small change. Okay, so if we calculate the GMs accurately, let me add a new color here. Maybe this green. So if we calculate GMs accurately using the equation IC over VT, 1.7 milliamps divided by 26 millivolts, that gives us 0.065 Siemens. So it's a little less than before. And for GM2, we have 3.6 milliamps divided by VT, and that gives us 0.138 Siemens, also less than before. Okay, so this is just to make sure that we have exactly correct values. All right, so going back to our main discussion, we need to ask the following question. We said that the higher the collector current, the better, the stronger the transistor is. So what price do we pay in doing so? Can I just give it higher and higher base emitter voltages and currents to make it a stronger and stronger transistor? Well, to a limit we could do that, but the price that we pay is power consumption. You can see that we have to have a higher current here than here to have a stronger transistor, to have a higher transconductance. And that amount of current has to come from some battery somewhere, and that battery drains out more quickly. So the trade-off that we have is between the power consumption of the device and the transconductance of the device. So we say trade-off between GM and power consumption, meaning how much current we drain from the battery. Okay, so it's good to remember that. We don't have infinite power available in any design, so that's something that eventually comes into the picture. Okay, very well. Let's see what else. Okay, so one other point is that from our calculations a moment ago, we realized that 10 millivolts, that 10 millivolt increment that came from the microphone and it was applied to the base emitter voltage was not considered a small value as far as calculating the slope is concerned. When we calculate the slope using this equation versus this change over 10 millivolts, we see that the values are a little different. So then the question is, when we say a small change in the base emitter voltage, what do we mean by small? What is considered small? Well, you can say 1 nanovolt or 1 picovolt or something, but reasonably, from an engineering perspective, what would be considered small? Well, it all goes back to this VT that we have here. So, for the change in base emitter voltage to be considered small, for example, this increment to be considered small, this change has to be a small fraction of VT. So that's also a good rule to remember because it often comes up in our calculations. So a small change in VBE, so if you want to consider it small, is equivalent to a small fraction of VT. In other words, if the base emitter voltage changes by 2-3 millivolts, that's pretty good, that's safe, and we can consider that a small change. But if it changes by 10 millivolts, that's not that small, so we cannot assume that we are calculating the slope of the characteristic with a 10 millivolt change here from here to here. All right, so that's another bookkeeping matter. And now that we have all of these, we can talk a little more about a few concepts, and then we finish this lecture. All right, so let's see how we calculate this GM anyway, how we calculate the slope. Let me show you the setup, the circuit setup that allows us to do this. So for GM calculation or measurement, this is what we do. We take a bipolar transistor and we place it in forward active region. So we connect a battery here. We connect the battery here. That's our VCE. That's our base emitter voltage. And we are measuring this current. So this base emitter voltage could be, for example, here. Now we increase this base emitter voltage by some amount, 1 millivolt, for example, right? So this base emitter voltage increases. I will put an arrow on it to show that it's variable. So we vary this by a small amount, and then we measure the change in IC, how much change we have from here to here. And that's how we compute the GM. So what you see in this measurement of GM is that the collector emitter voltage is constant when we are measuring GM. So that's something important to remember. So that means VCE is constant. So during GM measurement, the collector emitter voltage has to be constant. That's a very important point. Okay. All right. So that's all we have for today. What we have learned is that the bipolar transistor generates a current in response to a voltage. It's a voltage-dependent current source. And how much current change it produces in response to a voltage change depends on where we bias it. We bias it at a higher current, we get a higher transconductance, and vice versa. Now, what do we do with this current that the transistor generates? You have to pass the current through a resistor to generate a voltage, as we saw before. And this is something that we will pursue in future lectures. I will see you next time.